Okay, so let's have a little look here. So how about this first one? Okay, so what about a situation like this where we've got this car? Look what this car is going to do. There's a problem like this on the assignment also, 11.1 assignment. You don't even need the mass of the car. For example, on the pre-calc version of the assignment, I didn't even give you the mass or the braking force. You don't need either one. They'll cancel out. I want you to see how that works, maybe. Okay, so look, we're gonna lose 13 meters per second of speed. It's gonna slow down from 39 to 26 meters per second by applying a constant braking force, and it gives it to us, but we don't need it. The car then travels at constant speed for a while, and then it's gonna slow down again. It's gonna lose another 13 meters per second of speed. What I want you to do is I want you to give me the ratio of the distance it travels during the first deceleration compared to the distance it travels during the second deceleration, right? So let's just focus, we'll kind of color code this. Let's focus on this part, how about, when it slows from 39 to 26 meters per second. Almost all this stuff that we're dealing with here is just work energy theorem, right? We've got some one or more forces doing the work that changes the kinetic energy, right? So the work energy theorem tells us that the work due to all forces equals the change in kinetic energy, right? How many forces are acting on the car? They're doing work on the car, I should say.
Two.
What are they?
Friction and the
Driving force?
gravity.
Okay, so let's do a free body diagram for a second. So here's the car, right? We've got gravity pointing down. We've got normal force of the road pushing up, and we've got friction pushing in that direction. The displacement would then be in this direction, right? So which of those forces have components along the line of displacement? Not those, right?
Yeah.
Those are at right angles. So the only one that's really doing any work is friction. It's doing negative work because it's pointing in the opposite direction of displacement, right? Okay, so then the work energy theorem tells us right, the work energy theorem tells us, and we'll call this number, this is part one, right? So part one, we know that the work due to friction, so we'll call that F D1, how about, for the first distance, and that's gonna be negative, isn't it? Because the friction and displacement are in opposite directions, okay, is equal to the change in kinetic energy. So that's just going to be its final kinetic energy, which is 1/2 mv naught squared minus 1/2 mv, let's call this one, how about V1? Call that V1 is 39. Well, we could plug in numbers for this. Yeah, in fact, why don't I just plug in numbers? I'll just plug in numbers for them, just so we don't have to get so many symbols up here. Okay, so 1/2 m times 26 standard units squared minus 1/2 m times 39 squared, right? So there's the work energy theorem for the first slowdown. What about the second slowdown? So we'll make that one red. That's the one that's going from 26 to 13. But it tells us it's the same constant braking force, right? So the same frictional force, okay? So number two then,
Wait, is 39 and 26 are supposed to be in that order? I thought you said B naught.
well, yeah, I mean, we're going from initial is 39 and then it's 26. I'm just gonna put the numbers in.
So you're at 26 and B naught.
No, 39. Oh, did I have it back? Did I have V naught there?
Yeah.
Well, that was my fault.
Oh.
Changing kinetic energy is final minus initial, right? That was, right, exactly. Yeah, V1 minus V naught. Yeah, that was my mistake. So number two then here, we end up with, for the second situation, we get the same thing. Minus F, call it D2 this time, right? The work done by friction during the second slowdown is equal to 1/2 m times 13 squared minus 1/2 m times 26 squared, right? Okay. And so really all we're trying to do, we're just trying to get the ratio of d1 over d2, right? Okay. So if I were to solve for d1 in this first equation, I'm just dividing both sides through by negative f, right? And okay, yeah. To get rid of that negative, why not just multiply each side by -1? Right, so that's just going to make this one negative and that one positive and that one positive.
Doesn't that make the D
Uh-uh. Same thing down here. I could just multiply each side through by -1 and just change the signs, right? Okay. So then all we have up here, and I'll tell you a little secret here, you're going to find out at the end that it doesn't even really matter how we deal with the sign, because we're just going to take a ratio, and we're either going to get a positive number over a positive number or a negative over a negative. Same answer. Same answer either way. So if we solve for d1, we just get, I can factor out a 1/2 m, right? Times what? Then I'm going to get a positive 39 squared minus 26 squared over f. Right? Everybody see that? If I just divide each side through by f and I factor out the greatest common factor. I could put in, and I gave you mass, but we don't need it. And I gave you force, but you'll see we don't need it. This is actually a better way to do it. You can plug them in if you want. What about down here? Let's solve for d2. So d2 is going to be, let's go ahead and factor out again a 1/2 m. Divide both sides by f, so I get 1/2 m times, this is my positive term, and that's going to be my negative term, right? So 26 squared minus 13 squared, all divided by f. And I'm just going to take the ratio of those two things. Right? So my answer then is just going to look like d1 over d2 equals that. And really, I could just pull that f out in front with my constant. Agreed? So that just becomes all this stuff, and I'll kind of try to group this together. So all this stuff right here just becomes m over 2f times 39 squared minus 26 squared. What about the bottom? Same deal. Let's just group all that stuff together. So that's an m over 2f times 26 squared minus 13 squared. Well, look what happens. All the mass and the force cancels, right? All this stuff goes away. And so my answer is just that number. 39 squared minus 26 squared. I'm going to go up. Divided by 26 squared minus 13 squared. Okay. And then I've only got 2 sig figs, so I would just round that to 2 places. Okay. And so what's interesting about that is, let me get the calculator here. So do you think the ratio, even though we slowed down by the same amount, do you think the distances, the ratio is going to be 1? No. Which one do you think is going to cover a longer distance? Slowing down from 39 to 26? D1 is going to be a longer distance, isn't it? Yeah. So let's see what we get. 39 squared, 39 squared minus 26 squared divided by 26 squared minus 13 squared gives us 5/3. So if I turn that into a decimal, that's just what, 2 places, just 1.7, right? So you travel 1.7 times further during the first deceleration than you do during the second. Okay, how come? Well, because you've got more kinetic energy, right? Make sense? Okay. All right, so let's move on. Okay, how about something like that? So this is basically the same thing. I'm telling you, we've got a rifle that shoots a bullet, give you the mass of the bullet in grams, right? Got to turn it into kilograms. Gives you the speed of the bullet, right? It's going to travel through the air and it's going to get lodged in a wooden block, and the wooden block stops the bullet. Okay, when the block hits the bullet, it travels 44 millimeters into the block before it stops. So what we're trying to do is figure out the magnitude, so it doesn't need to be negative, just the magnitude of the average braking force. Right? So same deal, isn't it? Just work energy theorem, right? Change in kinetic energy, and the bullet loses all its kinetic energy. So the change in kinetic energy equals the work done by the block on the bullet to stop it, right? And so they're just trying to, I just want you to tell me what's the force, right? Does that make sense? Okay. So there's the displacement. You're going to find the force, and you can calculate what the change in kinetic energy is, because it ends up being 0. Right? Make sense? Okay.
Like the change in kinetic energy is 0.
No. It starts off with 1/2 mv squared and ends up with 0. So the change in kinetic energy is just whatever its initial kinetic energy is, it loses all of that, right?
Yeah, that's what I was meaning. I thought you said that. It's changed to 0.
No, it ends up at 0. Yeah. Well, I'll show you. We kind of set up the equation at least. So we end up with delta K, which is just going to be 0 minus 1/2 m, which we know, right? This is the mass of the bullet. So m v naught squared must equal the braking force. So we'll just call it F sub b times d, right? Because there's only one force doing any work on the bullet, and that's the block that's pushing on it, right?
And the distance is the 45 millimeters.
Yeah. Because this is what's happening when the bullet hits the block. It's got some speed. It loses all that kinetic energy, and the block is what's robbing it of that kinetic energy, right? It's pushing on the bullet to stop it. So the work done by the block must equal the change in kinetic energy. Okay.
So are we, on that equation, are we finding force?
You're finding force.
Okay.
So you're solving for that, right? Okay. Technically, this is negative because it's a frictional force, right? But remember, I'm just asking for the magnitude, so I just want to know, you're going to give me a positive answer, right? I just want to know how strong is the force. Okay. Whoops. All right. Okay, what about this one? So a bike rider approaches a hill on level ground at a speed of 10.7 meters per second. Let me just grab this one. I'm going to draw. So really, this is just a situation where you've got this level road and then you go up this hill, right? Okay, this is the stuff that we just talked, the only thing we really added in chapter 11, and this is it, is is just that in a closed system, mechanical energy is conserved, right? So all that's saying is my initial kinetic energy plus gravitational potential energy, so 1/2 mv naught squared plus mg h naught equals 1/2 mv final squared plus mg h final, right? So the sum of those two things is always going to be the same. Remember that we took the example with the ball in class. If you threw the ball up in the air, it was all kinetic at the bottom, but then it lost some kinetic energy, which turned into gravitational potential energy in the middle, and then it got it back at the end, right? So on this one, if we know this bike's kinetic energy, so down here, what we're probably going to want to do here is we can choose our reference point for height wherever we want to, wherever it's convenient. All we care about is the difference in height. So we're probably just going to let it equal 0 here, right? So we'll say at this point, h equals 0, and that's h naught. And then it's going to move up the hill to some point, and whatever that is, that's what we'll call h final, right? So down here, it's got kinetic energy, right? So we'd say the total mechanical energy is just going to be 1/2 mv naught squared plus 0, right? Because it has the height is 0. Up here, it's got no kinetic energy. It came to rest. And so that's 0 at the bottom, and that's 0 at the top. Whoops, backwards. That's 0 at the top, right? Because the final speed is 0. So do I need the mass? No, it cancels. It should. Think about this. Should it matter if Elijah's doing this or teaching? It shouldn't make any difference. If you're riding the same bike and it has the same amount of friction, right? Assuming it's frictionless like this is, shouldn't make any difference. Everybody should be able to coast up that hill to the same height if you approach the hill with the same speed, right? That's what the physics gods tell us, because the mass cancels. If I divide each side by m, it goes away. Yes, sir.
Alright, so to solve that, it'd be 1/2 times velocity squared, and then after you get that answer, you divide by gravity and you have your height.
Sure.
Alright.
Wait, why doesn't your mass affect the velocity?
Why doesn't it affect your velocity?
Like if you're approaching the hill, like what's your mass?
Okay, but we're assuming that our initial conditions are regardless of mass, this is your speed, right? So if you're carrying the same speed into the hill, your mass is irrelevant because it shows up on both sides of the equations. I could divide both sides, even with this original equation up here where I have 1/2 mv squared plus mgh naught equals same stuff on the other side. Look what happens to that equation. So 1/2 mv naught squared plus mgh naught equals 1/2 mv final squared plus mgh final. Well, I could do a couple things. I could divide both sides by m, so all the m's cancel, and I could even multiply each side through by 2 if I want to, right? I could make this equation simpler if I wanted to. If I were to distribute a 2 through both sides, 2 times 1/2 cancels, and so I get v naught squared plus 2gh initial equals v final squared plus 2gh final. So if we want to, I mean, we don't need to, but we could even write a new equation if we wanted to that relates initial and final velocities and heights. But we did it. It's just right here, right? This is probably the best way to do it because it's actually writing those energies. Okay? Make sense? All right, so another one I think that's real similar to that. It's like 2 for the price of 1. Oh, maybe not. Let me look at something. I think. the other one you could have got with this? There's two possible ones. The bike lost how many joules of energy to friction as it coasted up the hill? So this is the same kind of thing, right? This time it's not frictionless though. This time it's telling us that it approaches with a speed of 15.1 meters per second, and it travels up the hill 9.2 meters, right? So if I want to know how much energy I lost, I could go back to almost the same picture I had before, right? I could go back to this picture, and I could say, I could find the energy down there, it's all kinetic, right? And the energy up here is all potential. Subtract it, see how much it lost, right? You know what I'm saying? Okay. So I think you get a pretty good idea about this now. Same kind of thing here, right? We got rifle shoots the bullet again. Okay, it penetrates into the wooden block a certain amount. Now look at this though. It says the wooden block is resting on a frictionless surface. So what's going to happen? It's going to move, isn't it? How are you going to know how fast it moves? Okay, good. Momentum is conserved, right? So we know that the momentum that the bullet originally had, when the bullet gets lodged in the block, well now instead of it just being a 40.1 gram object that's moving along at speed, now it's got the combined mass of 40.1 grams, so 0.0401 kilograms plus 1.74 kilograms. That's my new mass. And the velocity must be whatever is necessary for the momentum to be the same, right? Does that make sense? So momentum before has to be the same as momentum afterwards, right? Because it's a closed system, it's just a bullet in the block. So you could figure out what the energy is going to be, or excuse me, what the speed is going to be of the block afterwards pretty easily. This is just conservation of momentum, but it's only in one direction, right? It's not like we have angles or anything here. And then if I want to know what fraction of the energy is lost, all I've really got to do is just figure out what's the kinetic energy before and what's the kinetic energy afterwards, right? Does that make sense? Okay. Because I'll know the combined mass afterwards, I can calculate the speed, 1/2 mv squared kinetic energy, right? And so what if, hypothetically here, how would we get this answer mathematically? Let's say we had something like before, let's just say it was 12,000 joules, and afterwards it was 2,000 joules. So how am I going to answer this? It wants to know what fraction of the combined energy is lost. How much energy is lost? 10,000, yeah, right, 10,000. So we lost 10,000 joules. So 10,000 joules divided by what we started with, right? Does that make sense? We started with 12,000 joules, we lost 10,000, and so what fraction is lost? Well, 10 twelfths or 5/6, yeah. 5/6 of the energy will be lost in that case. Right?
Convert that to decimal.
And, yep. Express your answer as a fraction, decimal, or percent. That's wrong though. I don't want you to do that, do I? I want you to, because you've got sig figs here. Let me change that right now, 'cause that's wrong. So you're just gonna write it as a decimal. Or percent would work too. So, Except a fraction, no, there is, because a fraction implies you can only keep a certain number of sig figs. Before I forget, let me fix this.
Is it just the wording or the actual formula of that?
No, it's a good question. I better look. Yeah, I think that's it right there. No.
Mr. Roy, do you have to leave as soon as the bell rings?
No.
Can we stay on then?
Yeah, absolutely. No. I don't have track anymore. I'm fine. I can. Okay, here it is.
Hey, Mr. Webb, who's the trebuchet?
So, you guys are so busy. I think we're just gonna, if we can do it Friday, we'll start Friday. If we can't, we'll just go Tuesday and whatever time we have Wednesday. Yeah. I'll set it up so it can't hurt you. How's that?
Let's do, we'll do it 282.